Okay, hello, welcome back to the lectures in turbulences. Here you can see some kind of weight regions in a pipe. And I've told you that it depends pretty much on the type of fluid flow that is inside the pipe, and it depends pretty much on the direction in which the pipe flow occurs. If we come from the smaller part to the bigger part, you see some wake regions here behind this edges. If you come from the other side, you turn this pipe around and the fluid flow comes here from the left side. The wake regions are pretty different. Now you have other turbulent regions, and so the same part has different turbulent regions. And that's something that occurs pretty much in technology, and that is often a really big problem in technology. And I can give you a short example of my life as engineer. When I were in the company, I had here an examination, a CFD examination. And here you see a small throttle region for gasoline. Yeah, this was for gasoline filter, and the gasoline enters this smaller pipe region here. Yeah, it enters here, it exits here, and this was the entry of a filter, and we always had damages at the filter, at the sides. And I made CFD simulation with two different mesh sizes, and you can see that this region was pretty small. It was just a few millimeters in diameter, but I used a lot of different hexaeder cells to model this throttle. Yeah? Here I used the fine mesh and I used the coarse mesh. And now if you look at the results here, you can see the CFD results. We first have a wake region here, and then we get here a swirl, yeah? And we get also swirl at the exit, and you see a fluctuation. And you can also see that the simulations results are quite different if you use different meshes. Yeah, so description of the turbulence changes pretty much if you change mesh size. If you use a fine mesh, the discretization of the swirls are much better. If you use a coarse mesh, the fluctuations are much look quite different. And the problem was we had a damage here at the walls, and this damage only occurs because of the fluctuations inside the fluid flow. So the turbulence can pretty much influence the design. Yeah, and so we changed here the geometry a bit to get less fluctuations. How can we describe this fluctuations? Yeah, so you have the velocity, for example, in our pipe or in our nozzle, and we have normal the mean value of the velocities. That's logical, yeah. If you just make a calculation of fluid flow, you have a special volume flow, and you have a straight velocity, and yeah, that's it. And here you see a fluctuation, yeah. You can also see it in the results, yeah. You have this fluctuation of the velocity, and now you can also make describe this by a deviation of the mean value. Yeah, you can describe the mean value of the velocity, and you can describe the deviation, yeah, that is influenced by the fluctuation. Here I have summarized this. Yeah, we have stochastic momentum in the fluid region. Yeah, we have our velocity. This velocity depends on X, Y, and Z coordinates and on the time. And you have your mean value. Yeah, you have your mean value of the velocities, and you can have additionally the deviation. And the mean value gives you a description of the mean velocity, but the deviation gives you an impression of the fluctuation of the fluid. This can be fluctuation occurs in the velocity and the momentum, but it also occurs in the pressure. Yeah, if you remember Bernoulli's law and remember the energy balance, all the quantities that you have in the velocities, you will find them again in the pressure field. So you will also have a mean pressure and a deviation, a fluctuating deviation of this mean value. Yeah. Mean value and deviation, I summarize. In case of turbulent flows or fluid flow with physical quantities, velocity and pressure, they're split in two different fractions. You have a stationary time-dependent mean value, and you have an instationary fluctuation of these mean values. Yeah. Look, we look in the cell. If we have our cell, you remember this example I always made for this hexahedral cells. Yeah, you have here your dx value, your dy value, and your dz value. That gives you the volume of the cell. And you have your U mean value, you have your V mean value, and you have your W mean value. This is more or less defines your volume. And now you can also have a mean value velocity, but you can inside the cell, the velocity can change a bit. Yeah, you can have this fluctuating values, this fluctuations. This gives you the turbulence. And based on this fluctuations, on the deviations, we can formulate the so-called degree of turbulence. Degree of turbulence is defined by 1 divided by mean velocity multiplied by square root of the vector product of this fluctuations. Okay, though if you imagine you have big fluctuations, yeah, if you have high deviations, the fluid is fluctuating very fast, then you have big deviation values, and then you can, yeah, and then you can have big turbulence degrees. If you have small deviations and small fluctuations, you have small degrees of turbulence. So this degree of turbulence is also isentropic. Yeah. So isentropic means no, the velocity components does not have a direction anymore. Yeah. If you calculate this turbulence number, you don't have a real direction anymore. This is, yeah, here you have the direction of the deviation. It goes in this direction or in this direction or in this direction. But if you build the square root, the direction is, yeah, is gone. This. Okay. So this is a turbulence number. And now look a bit on the size of the swirls. Yeah, you have your U velocity, you have your mean velocity, and now you can have big swirls, yeah, really big swirls with a characteristic length, and you can have small swirls. Yeah, you can have small swirls like this. Okay, and you can imagine if you make a mesh, you have to describe this. You can really easily describe the big swirls. You can just solve momentum equations. But if the swirls get smaller than your mesh size, you cannot really describe them anymore with a momentum balance. Yeah, you will have difficulties to describe it. And then you need a so-called turbulent viscosity. Yeah, you define this turbulent viscosity is defined by turbulent kinematic viscosity divided by density. And the turbulent viscosity gives you a hint about the shear stresses inside the fluid. Yeah, so I try to explain it with my own words. Yeah, you describe with a momentum balance the big swirls, but you describe the small little swirls not anymore with a momentum balance. You describe it with a kind of viscosity, because if you have a lot of small swirls inside your fluid, it behaves like if viscosity is higher. Yeah. Remember, viscosity describes you the thickness of the fluid. For example, if you have a high viscous fluid, the fluid is getting thicker and so and like honey. And if you have many swirls inside the fluid and many turbulence, the fluid is getting kind of the viscosity rises. Yeah, it's getting, it is more like honey. It is more thicker. Okay, and this has to be modeled. So it is modeled by a so-called turbulent viscosity. So turbulent viscosity, and then we have another quantity. We have the so-called turbulent kinetic energy. Yeah, and this turbulent kinetic energy is based of the so-called K epsilon model. Remember ANSYS? I scroll back. In ANSYS, you see here we had the screen. You remember this? We showed the convergence of K, so turbulent kinetic energy, and E equation, it's the so-called dissipation of the turbulent kinetic energy. What does this mean? Let's go back to the slide. It means if you have high fluctuations, if you have high differences of velocities and high swirls, you get this K value, you get high kinetic energy. So you describe the fluctuations of the different velocities. You describe them just with one value, with the energy value. And also with the fluctuations of the U's, you describe them with this small k value. Okay. So I try to describe it. If you have your cell here, yeah, you have your swirls, you have your big swirls, you have your small swirls, and normally if you make a mesh of it, you can describe every single velocity. But here the swirls are smaller than the velocity quantities, and then you just make a mean value, a square root of all these quantities, and then you just get one value for the whole energy inside this cell. Okay, Mr. Martin, can you stop the recording?